To solve number 5, we're looking at a combustion reaction involving propane, which is this, and it's producing carbon dioxide and water. So the balanced reaction is as follows. Propane plus O2 will produce CO2 plus H2O. Now to balance that, to save you the details, a 3, a 4, and a 5 will do that. Now, as you recall from what we talked about yesterday, that these numbers are not only mole ratios, but they also can be volume ratios. So I know that if I have 34.4 liters of carbon dioxide, and I want to know how much propane I used, I just can do a quick ratio of 3 liters of carbon dioxide to 1 liter of propane. So 3 liters of CO2 to 1 liter of propane. So I take my 34.4 and divide it by 3, and I get a nice 11.5 liters of propane. The next problem. How many grams of sodium are required to produce 31.9 liters of hydrogen gas? Now we also have a pressure and a temperature. Now right away when you see pressure and temperature, you're going to think of ideal gas law, or you should. We know our pressure is 97 kPa. Our volume is 31.9 liters. Now we don't know moles. We know our ideal gas constant is 8.31 and our temperature is 290. So we're going to solve for moles here. And you've been doing this enough that I don't need to go through the steps of solving. But when you multiply these two and divide by the other two, you should get an answer of 1.3 moles. And this is of hydrogen, because we're talking about hydrogen gas and all this. All right, so this is how many moles of hydrogen gas we got. Now our goal is to get to grams of sodium. So now we just use the balanced reaction here to get there. So I know I have 1.3 moles of hydrogen gas. I have 1 mole of hydrogen gas per 2 moles of sodium. And then the next step is just to find the molar mass. 1 mole of sodium, 23 grams of sodium in a mole. That's the molar mass of sodium. And now we just go through the calculations of 1.3 times 2 times 23, and we get 59.8 grams of sodium. Now we want to have only 2 sig figs because of the 290, so we want to make this 60. Make sure you put that decimal in there to make it significant, grams of Na for our final overall answer. And then our last problem, we're talking room temperature and at pressure. We have this many grams of octane, and we burned it with oxygen. So again, another combustion reaction. So without a balanced reaction, that's the first thing we have to produce here. When we take octane and add oxygen to it, we still get the same products in combustion, carbon dioxide and water. To balance this, you have to do a little bit of work. I'm going to help you out with the balancing so you get here. So it's 2, 25, 16, 18. So give us some really weird ratios and some really big numbers maybe. So we look and we have temperature and volume. We want to find liters of product. So our first step is to get to moles of product. So we have 381 grams of octane. Now, we know that this is going to be our limiting reactant because of the word plenty of oxygen gas. The molar mass of octane, carbon's 12, we got 8 of those. Add 18 more to it, it's 114 grams in 1 mole. So octane is here. Now to get to moles of octane, I take 381 and I divide it by 114. And with my 3 sig figs here, I should have 3.34 moles of octane. Now I want to get the moles of each product. So again, I go to my mole ratios, 2 moles of octane for 16 moles of carbon dioxide. 2 moles of octane and 16 moles carbon dioxide. So 3.34 times 16 divided by 2 gives us 26.7 moles of carbon dioxide. And then our last step is to use the ideal gas law, PV equals nRT, to solve for volume of gas. Our pressure is 100 kPa, multiplied by V is equal to our moles of carbon dioxide, 26.7, times our constant, times our temperature in Kelvin. It's 25 Celsius, so I have to add 273 to it to get the Kelvin, 298 Kelvin. And then I want to solve for volume. Sorry about that. 26.7 times 8.31 times 298, all divided by 100, gives me 661 kPa. Now with sig figs, we're looking at 1 sig fig for our answer, so it'd be 700. But we will we'll keep it at 661 just so we can make sense of the number. Then for water, same steps. I want to start here with my 3.34 of octane, and it's 2 moles of octane to 18 moles of H2. And then when I do that math, 3.34 times 18 divided by 2, 30.1 moles of H2O. And then we go back to ideal gas law. Conditions the same. And our conditions are as follows. Our conditions were 100 kPa times V equal to 30.1 moles of water. 8.31 is our constant. And our temperature is the same, 298. And then we just go ahead and solve away. And our volume of water should be 30.1 times 8.31 multiplied by 298 divided by 100. And I get 745 liters. I'm sorry, this kPa should be liters. Hopefully you caught that. And then we show that many liters of H2O and this many liters of carbon dioxide.